Greetings, this is Greg. The FW-190 was a very good airplane, but the plane's specifications don't really tell the story. If you look at the 190 by the numbers, it's generally mediocre. However, if you look at it in terms of effectiveness, it's another story. German ace Gunter Rahl said in an interview, and that interview is on YouTube, that when you hear about a German pilot shooting down 13 or 14 airplanes in one day, they were usually flying an FW-190. There are reasons for that, and I plan to cover them in this series. The FW-190 was designed by a man named Kurt Tank. He was a young man during the First World War. He wanted to enter the German Air Service, but due to family tradition, enlisted in the cavalry. Of course, in World War I, cavalry units, for the most part, eventually became almost indistinguishable from infantry and other units. He won several medals for bravery and ended the war as a captain. I'm mentioning this because his experiences in the First World War had an effect on his design philosophies. After the war, he was educated in Berlin in electrical engineering, and he learned to fly around the same time. Then he got a job working on flying boats, and later assisted in the design of the Rohrbach Roland. This is the type of plane Hitler flew during the first portion of his 1932 election campaign. Next, Kurt Tank went to work for Albatross as a test pilot. Yes, this is the same company that built the famous Albatross fighters from the First World War. But after the First World War, they kept building airplanes, like the L-73 shown here, but never had a design that was really successful in a commercial sense. Even among aviation enthusiasts, you would be hard-pressed to find anybody that can name a post-World War I Albatross aircraft. Of all the post-war planes they built, this one, the L-82, was built in the highest numbers, still only 72 examples being produced. So as you can imagine, Albatross went bankrupt. That happened in 1929, and under government pressure they merged with Focke-Wulf in 1931. Since Tank was at Albatross, now he's effectively working at Focke-Wulf. He worked on the FW-44, which was a biplane trainer. It came out in 1934. It's somewhat similar to the Stearman in the U.S. This was Focke-Wulf's first commercially successful airplane. As a point of interest, it was actually used in combat in the Second Sino-Japanese War in 1937, and that sort of became World War II, so it, by some standards, you could say it actually was a warplane. In any case, it was successful. They sold a lot of them. Now, Kurt Tank then designed the 200 Condor, which first flew in 1937. Had the war in Europe not broken out, this probably would have been developed into a fairly successful airliner. There are a few things of interest here. First, I think it's how impressive Focke-Wulf went from designing relatively simple biplanes and parasols to a complex four-engine airliner that could cross the Atlantic. Second, Tank's field of study in school had been as an electrical engineer. Therefore, he must have learned about aircraft design literally on the job. Actually, now that I think about it, it's not that unusual for a person with a high level of math skill to be able to work, or be able to move, let's say, from one field of engineering to another. There are other cases of that happening. In 1934 and 1935, the German Air Ministry, or RLM, held a contest to choose a modern fighter for the Luftwaffe. Various planes entered, including the Messerschmitt Bf-109, which, as we all know, eventually won. The Arado 80, it had fixed landing gear, thus no chance here. The Heinkel HE-112 shows up to the party. Focke-Wulf showed up with this, the parasol-winged FW-159. Now, I don't know what they were thinking, but it seems Focke-Wulf tried clinging to that parasol design way too long, and the 159 had no chance in this competition. The Bf-109 won pretty easily, with the only real competition coming from the HE-112. We need to talk about the HE-112 a bit more, not because it had any real impact on the war, but because its relationship to one of the FW-190's main antagonists is relevant. Just after World War I, the Treaty of Versailles prohibited Germany from building powered aircraft. So initially the Germans focused on gliders, but eventually the restrictions were relaxed and powered non-military airplanes were allowed. Some German firms like Heinkel built airplanes that, while intended for civilian use, could be converted for military purposes. The most famous example is probably the Heinkel 111, which really just masqueraded as an airliner, and it became one of the Luftwaffe's primary bombers. What's not as commonly known is that prior to the 111, Heinkel built the HE-70 mail plane. It set several speed records. It was legitimately a mail plane as well as a passenger plane. It had some but minimal use as a reconnaissance plane and as a bomber. Take a look at the HE-70's wing. That elliptical shape may look familiar. This man, a German named Ludwig Prandtl, doing the best I can on that pronunciation, was a leading aerodynamics expert and a big believer in the elliptical wing design. He wrote several NACA reports in the 1920s that talk about the advantages of the elliptical wing. His writings are still relevant today. Here's a quote from Aerodynamics from Naval Aviators. That says a lot. They're still talking about his work. Here's a recent NASA report which also refers to Prandtl and discusses the elliptical design. Enter a Canadian man named Beverly Shenstone. In 1929, he moved to Germany, where he worked for Junkers, became lifelong friends with Alexander Lippisch, and met Ludwig Prandtl. Thus, he knew his way around German aviation circles and, most importantly, knew of Prandtl's thoughts on the elliptical wing design. In 1932, Shenstone moved to Britain, and as you have probably guessed, went to work for Vickers Supermarine. Now, Reginald Mitchell, who was the designer of the Supermarine Spitfire, it was a project he was working on at this point, tasked Shenstone specifically to bring an external perspective to Supermarine's designs. To further that goal, Shenstone traveled back to Germany, then to the U.S., where he met with various manufacturers and NACA. He then took the latest NACA information back to Supermarine. This included the latest NACA 2200 series wing designs. Shenstone was doing the smart thing here, gathering the best and latest information on aircraft wings. So let's take a look at that Heinkel mail plane again. Clearly from the top, the wing looks a lot like the Spitfire's wing. So was the Spitfire a copy of a German design? Well, here's what Shenstone says on the subject. Quote, "It's been suggested that we at Supermarine had cribbed the Spitfire's elliptical wing shape from that of the German Heinkel 70 transport. This was not so. The elliptical shape had been used in other aircraft, and its advantages were well known. Our wing was much thinner than that of the Heinkel and had a quite different section." Unquote. Well, it's my opinion that that's a very carefully crafted statement. Nothing he says is wrong, but as a whole, I think it's a little bit, it could be read a little bit wrong. Let's go through it. Yes, it has been said that the Spitfire's wing was copied from the Heinkel 70. That's because from the top, the elliptical shapes are incredibly similar, as we'll see. It's true that the elliptical shape had been used in other aircraft. Some Japanese aircraft are quite similar, but so what? That seems like saying that everybody else was copying the Smart Kids test, so it's not really copying anymore. That just doesn't make sense. The similarity with Heinkel, the Heinkel wing, is beyond being simply a similar elliptical shape. Not only do both planes have elliptical wings, if you look closely, both are actually two different ellipses together, with the forward section being the more narrow of the two. Now the Spitfire's wing is thinner. Yes, they have two different sections, but wing planforms, various types are seen here, are very different things from wing sections as seen here. All Spitfire wings use the NACA 2200 series section, the exact type Shenstone learned about on his visit to the U.S., and Shenstone himself says that. Now, sources for all this are in the description, but I think it's incredibly obvious that the wing plan form of the Spitfire was very heavily influenced by the Heinkel 70. No, it's not an exact copy. It couldn't be. It's used on a different airplane. They needed to put guns in the wings. It needed to go faster because there was more power available, and it was a fighter plane. Had to deal with different conditions, higher speeds, G-loads, and so forth. But its relationship seems clear, especially in light of Shenstone's history working in Germany. Furthermore, the cross-section is straight from NACA. That's not in dispute. Thus, the Spitfire's most famous feature, its beautiful elliptical wing, actually had its origins in German and U.S. designs. The brilliance of the British in this case was in actually building and mass-producing it. It's very difficult to make an elliptical wing, and Supermarine did a fantastic job. So, while the HE-112, I guess that's what we were talking about, was itself influenced by the HE-70, it never really went anywhere, and it's incredibly ironic that the main competitor to the BF-109 and FW-190 was heavily influenced by German designs. I think had the HE-112 been given the chance to develop, and especially had they switched to a later NACA section, it would have been superior to the 109 in terms of performance. But we'll never know, and I think that was enough of a diversion, so let's get back on track. In 1937, so this is only a few months after the Focke-Wulf 200 Condor's first flight, the RLM sent out a request for a second airplane design to fight alongside the 109. Kurt Tank submitted multiple designs. I have a feeling that he really wanted to win this contract, but he didn't get any traction until he submitted a design using an air-cooled radial engine, specifically the BMW 139. At this point, the German Ministry of Aviation, or RLM, became interested. Most German fighter proposals at the time were designed around the Daimler-Benz DB601. The 601 was a fine engine, but it was complex and time-consuming to build. There just were not enough of them to go around. Thus, any new fighter using the 601 would have to rob supply from production of some other aircraft. This was undesirable for obvious reasons. On the other hand, BMW's air-cooled radial engines were not in much demand at all. Most European aircraft manufacturers had been shying away from radials, especially for land-based fighters. It was thought that the drag from a radial would hurt performance too much. Tank felt that the drag issue was far from insurmountable and had some interesting plans to deal with it. Regarding the design in general, he said this, and I think this is pretty important. Quote, "The Messerschmitt 109 and the British Spitfire, the two fastest fighters in the world at the time we began work on the FW-190, could both be summed up as a very large engine on the front of the smallest possible airframe. In each case, armament had been added almost as an afterthought. These designs, both of which admittedly proved successful, could be likened to racehorses. Given the right amount of pampering and easy course, they could outrun anything. But the moment the going became tough, they were liable to falter. During World War I served in the cavalry and in the infantry. I had seen the harsh conditions under which military equipment had to work in wartime. I felt sure that a quite different breed of fighter would also have a place in any future conflict. One that could operate from ill-prepared frontline airfields, one that could be flown and maintained by men who had received only short training, and one that could absorb a reasonable amount of battle damage and still get back. This was the background thinking behind the Focke-Wulf 190. It was not to be a racehorse, but a strange German word, a cavalry horse." Unquote. In this episode, I want to cover the design factor choices that made the 190 more of a cavalry horse than a racehorse. At the beginning of this episode, I said the 190 had generally mediocre performance. I should clarify that. I was talking about overall performance throughout the war. There are certain time periods and in certain areas where the 190's performance was generally superior. In this series, we'll go over a lot of performance information, but it's not the focus of this specific episode. First, we have the landing gear. It's wide, really wide. Obviously, this makes it very stable, unlike the 109 or Spitfire. In World War II, many fighters were lost in takeoff or landing accidents, so making this easier is quite meaningful. An often unmentioned advantage is that it's easy to tow the plane. Most airplanes have towing instructions with all sorts of limitations and warnings. The FW-190's manual simply says attach the tow ropes to loops on the upper shock struts and pull it around with either people or a vehicle. One person at the rear, as seen in this picture, steers the tail wheel with a forked bar. There are several drawbacks to the wider gear. It makes the plane heavier due to the extra structure required since the gear is attached farther from the fuselage, and it doesn't allow you to roll the fuselage around by itself without the wings attached. This can be a drawback on the assembly line or for rail transport, although I don't think that drawback played in much during the war. The 190's tail wheel is retractable, but it doesn't really retract fully. The reason is so that it can act as an emergency skid, and I think this one factor kind of shows the whole design philosophy of the airplane. They sacrificed a bit of performance here. They could have made it retract all the way, but they sacrificed that for the real-world situation they felt the plane would encounter. If the tail wheel doesn't extend, the plane will be quickly fixable and back in action. Overall, I think the wide-tracked gear is a huge plus for the 190. The landing gear is also very rugged. It could withstand a landing with a sink rate of 4.5 meters per second, or 900 feet per minute. Let me put that into perspective. A 190 on a normal approach to landing with a glide path of about 3 degrees, which would be typical, will have a sink rate of about 550 feet per minute. So even if the pilot did nothing with the controls to soften the landing and just flew that path down until he hit the earth, he would only be descending at 550 feet per minute, and the plane is built to handle 900 feet per minute. Operation of the landing gear is incredibly simple. There's a button for extension and a button for retraction. The retraction button has a guard over it to prevent accidental activation on the ground. By this time, most fighters had reasonably easy to use landing gear systems. There are some exceptions, of course, but the 190 is about the easiest. For example, the P-40 has a few extra steps, but it's not horrible. Now, if the 190's electrical gear extension system fails, the emergency gear extension is also easy to operate. The pilot pulls one lever, gravity does the work. This would be comforting if bringing in a damaged airplane. So, although it sacrifices some small amount of performance, the 190's landing gear is rugged, easy to operate, reduces takeoff and landing accidents, and makes the plane really easy for ground crews to move around on the airfield. This all seems to be in harmony with Kurt Tank's idea that it should be more like a cavalry horse than a racehorse. The flight controls on the 190 are fairly unique in that they were operated by push rods supported by bearings, rather than cables and pulleys, which were more typical at the time. Now, there are cables in the 190's control systems, but their use is minimized. The drawback of cables from the pilot's standpoint is that they stretch, degrading the feel of the controls and causing variations in that feel from plane to plane, sometimes even in the same plane from one flight to the next, especially if maintenance has been involved. We're going to go over this diagram of the elevator control system. At position 1, we have the control stick. It's conventional. It connects to a torsion bar at position 2, which transmits the fore and aft motion of the stick to a push rod at position 3. This push rod connects to a bell crank at position 4. That bell crank is solidly attached to a bulkhead. So far, the system is really solid, no real chance of stretching or slop developing. Now, from that bell crank, we have two control cables at position 5, which go to the elevator differential control unit at position 6. We're going to come back to that because it's important. From here it's easy: 7 push rod, 8 a bell crank, 9 another push rod, 10 the elevator actuation lever, and 11 the actual elevator. So the majority of the motion and direction changes are handled by push rods. But we have those cables at position 5 and the differential control unit at position 6. What's that for? Well, the differential control unit is there to make the plane a bit easier to fly and, in my opinion, would improve gunnery. What it does is reduce the amount of control surface deflection for a given amount of stick travel when the stick is near the control surface neutral position. This allows for a greater amount of control precision when making small changes from neutral. Both the elevator and rudder have this system in most 190 variants. I can't pin down every variation of this airplane. They built so many. I think that all A models have this except for the rudder controller on the later A8s. I know for sure A5s have it in most A8s. Pitch trim is accomplished by means of an electrically operated horizontal stabilizer. I really like this system. In this picture, I added some colors for clarity. I circled the electric motor that moves the stabilizer. The blue line is the leading edge of the stabilizer. The motor spins, operates a worm gear and drive spindle to move the front of the stabilizer up or down, to add either nose up or nose down force. Most World War II fighters, like this P-51, use a simple trim tab to relieve control system pressure. The pilot adjusts this for varying flight conditions, typically by spinning a wheel that's connected to the tab by cables. The 190's trim system has several advantages, and by the way, it's the system that's most commonly in use today. First, in commercial type aircraft. First, it not only relieves control system pressure, it increases pitch authority. As an example of why this might matter in a 190, if you have battle damage, say you lose an elevator and can't keep the nose on or below the horizon with elevator alone. In a 190, you might be able to save the plane by giving it pitch trim. The trim system is easy to use. It's controlled by a fore and aft moving switch located here at position 8. The switch is spring-loaded to the neutral position. When the system reaches its travel limit in either direction, the motor shuts off so pilot error can't burn it out. Position 7 shows the stabilizer position, which would be checked against the markings on the tail by either mechanics or during the pilot's pre-flight inspection. That's important because that way you know it's in the right position relative to the indicator in the cockpit. If those two things were not in sync and you just hopped in the plane for takeoff, when you set your trim to the takeoff position, the stabilizer might not actually be there. So that's the reason for those markings on the airplane, and they all have it. Now, the Aileron system uses no cables at all. Ailerons use only rods and bell cranks, and everything's riding on bearings, so it's really nice. As with most contemporary World War II fighters, the 190 uses Frise-type ailerons. These are hinged in such a way that the leading edge of the up aileron moves down into the slipstream to increase drag. Why would we want to do that if it increases drag? Because it reduces adverse yaw. You may recall from earlier videos here that the down aileron creates more drag than the up aileron, causing the plane to yaw when the ailerons are moved. This reduces that adverse yaw by partially equalizing the drag between the up and down ailerons. Doesn't truly equalize them, but it brings them closer together in terms of drag, thus reducing the amount of rudder needed in some maneuvers. It's a good thing, which is why many World War II fighters were built this way. This type of aileron also increases effectiveness, especially at higher angles of attack, and reduces control forces. The 190's aileron system has relatively light control forces due to the specific Frise design and the rod and bell crank system, and of course the use of bearings. The only real downside to the 190's primary flight controls, meaning elevator, rudder, and ailerons, was a lack of trimming ability on the last two, the elevator and rudder. Trimming of ailerons and rudder was only possible on the ground by bending trim tabs. Notice the little red tab on the back of the rudder. That's the trim tab. They work opposite of how you might think. For example, if your plane requires right rudder in cruise and you want to dial that out, you bend the tab to the left. This is because moving it to the left forces the rudder to the right. There's a trim tab for the ailerons and for the elevator. You might wonder why there's one for the elevator when it has that movable stabilizer. It's for fine-tuning the airplane. If the plane requires an odd amount of pitch trim, it can be adjusted out with this tab. Typically, these would be set up on test flights when the plane was new and generally not messed with after that unless the plane suffered damage or needed to be repaired for some reason. Most U.S. aircraft had trim tabs for the aileron and rudder that could be adjusted from the cockpit. That was much less important in German fighters because they didn't stay in the air as long. So pilots could adjust the trim for cruise flight and just accept that they would have to use some rudder pressure during other conditions, same with ailerons. So while as a pilot I would rather have aileron and rudder trim controllable from the cockpit, I understand why the 190 doesn't. It saves weight, complexity, and construction and maintenance time, and isn't really needed in this application. Many general aviation airplanes are set up the same way and it's not a problem. I'll also add that I've seen statements saying that the 190 didn't require much trim change with variations in speed or power. So pilot-controlled trim tabs for these things were just not needed. I'm not sure I'm buying that, but of course I haven't flown a 190, so maybe it's true. Let's move on to the flaps. They're located here at position 2, but on the underside of the wing. They're not visible from the cockpit. Here they are in the fully extended position. They are of the split flap design, which means they tend to create a relatively high amount of drag with a relatively low increase in lift as compared with other types of flaps. We'll get to what that means in terms of performance in a later episode. They are electrically actuated, like almost everything on this airplane. Each flap has its own motor that drives the flap via a worm gear. The two motors are synchronized with each other, so the flaps move together. Pilot operation of the flaps is easy. There are 3 buttons, numbered 2, 3, and 4 on this picture. The middle button is the takeoff position. The other 2 are up and fully extended. The position indicator lights are at position 5. Now, provided the plane is at or below maximum flap speed, all the pilot has to do is press the button and the flaps drive to that selected position and stop. In the event that the flap position indicator lights are inoperative, there is a small window in the wing, seen at position 3, which allows the pilot to see the flap position. The flap controls are very near the throttle lever, as are the trim controls. Let's go to a cockpit diagram so you can see that. The throttle lever is circled in green, flap controls in red. So you can see how easy it would be to move your hand off the throttle in a dogfight, even during high G maneuvers, and select flaps entirely by feel, thus keeping your eye on the enemy. You might think that would be the common way to do it, but it really wasn't. The 190 was one of the first planes to set up the cockpit with the pilot in mind. For example, here is the flap control lever in the Spitfire. That lever will be very hard to manipulate during a 4G turn. This may not seem like a big factor, and by itself it really isn't, especially in the Spitfire because its flaps are only up or down, and believe me, the down position is not going to be used all that much in flight, other than for landing. But the point here is that the 190's entire cockpit is set up this way. We'll talk about it more later on. And this allows the pilot to focus more on the fight, less on the airplane controls, and all of these little things add up. The flaps themselves are interchangeable left and right, which simplifies the spare part situation. Mechanics can easily adjust them via an adjustable push rod accessed through a service panel on the lower wing. Both halves of the elevator are interchangeable as well. Thus, the flaps are easy to use, easy to service, can be manipulated in combat easily, even under high G loads. Now, you may have noticed that all of the powered controls we've talked about so far, the elevator trim, flaps, landing gear, are all electric. In most other fighters, these things are usually hydraulic, mechanical, or pneumatic. Pneumatic means operated by air pressure or sometimes suction. Kurt Tank believed that the electrical systems would be more reliable than hydraulics. In my experience, they usually aren't, but Tank was an electrical engineer, so I think he had more faith in electrical systems than I do, and certainly more than he had in hydraulic systems. Tank also thought electrical systems would be less susceptible to battle damage than other types. I think he was right about that. Just as an example, if in a 190 your flap motor gets hit, you lose control of the flaps, meaning they'll be stuck in whatever position they're in, hopefully up, but you didn't lose anything else. This is in contrast to most hydraulic systems. For example, this is the diagram for a P-51D's hydraulics. Hydraulics in this plane are used to operate the brakes, landing gear, and flaps. The 190 uses hydraulics for the brakes also. Now, this system in the P-51 operates at 1,000 psi. A hit to the pump, lines, or most of the components will cause the fluid to blow out in seconds. Thus, you'll lose the ability to control both gear and flaps, although you should still be able to extend the gear via the emergency gear release, just not retract it again if you needed to. The brakes are on a separate system. Even if the reservoir is empty, the brakes are still going to work, unless, of course, they take direct damage. Now, this is a diagram for the P-51A. Similar, but with two significant differences. The 51A's hydraulics also control the radiator scoop, and there's a hand pump which can be used if the engine-driven pump fails. However, if it takes battle damage and the fluid blows out, you lose control of flaps and that radiator scoop and the ability to retract the gear, and the hand pump won't help you. As you can see, there are hydraulic components all over the place. Lines run from the engine compartment all the way back to the tail wheel and in the inboard sections of the wings. Most U.S. fighters were similar, with hydraulic systems operating gear and flaps and being interconnected. It's not too bad. Some other fighters were much more vulnerable. Let's talk about the Spitfire. I've been wanting to have this discussion for a while anyway. I often use the Spitfire for performance comparisons, primarily, well, for two reasons. One, it fought throughout the whole war, and also there are so many versions of the Spitfire that there's usually a contemporary version to compare to whatever I want to talk about. And in these comparisons, it usually comes out very, very well. It was probably the most maneuverable fighter on the Western Front. Maneuverability is a little bit hard to define, but I would say that yes, the Spitfire was the most maneuverable fighter on the Western Front. Now, in terms of speed and rate of climb, it's usually near the top of the list. It has great firepower, especially if it's packing the 20mm Hispanos. And it has the highest Mach limit of any propeller-driven fighter of the war. If you go through the videos of this channel, with a few exceptions, the Spitfire always seems to come out on top, or at least near the top when we're talking about performance. It might look like I think that the Spitfire can walk on water. However, I don't think that. All that awesome performance comes at some cost. The Spitfire relies heavily on a pneumatic system using pressurized air to run various subsystems. There's an air pump, which pressurizes two tanks located behind the cockpit in most variants. They provide air pressure to these subsystems. This page from the Spitfire 9 manual shows the subsystems are brakes, cannons, flaps, machine guns, radiator flaps, and supercharger gear change. Damage to this system can easily render the entire thing inoperative, and when that happens, the Spitfire is out of the fight because it can't fire its guns. If it's at high altitude and the supercharger switches back to the low gear, now it can't fire its guns and it can't really run away. That's going to be a problem if enemy airplanes are nearby. There are many partial failures possible as well. For example, in some cases, a smaller leak can mean that when you put the flaps down, the brakes will become inoperative. So while the Spitfire's performance was truly awesome, as with all airplanes, it has some downsides. It's not all sunshine and rainbows for the mayor of Spitfire Town. Now, we know that Kurt Tank's vision for the FW-190 was very different from that of the 109er Spitfire. It was influenced by his experiences as a soldier in World War I and by his education in electrical engineering and, of course, his experience as a pilot. He chose to make the plane easy to fly, easy to maintain, and rugged. He provided the pilot with excellent, precise flight controls with increased precision near the elevator and rudder neutral points. Anyone who has ever fired a rifle knows that when firing at a target 300 meters away, a very slight movement of the gun will put the sights way off target. So the extra precision and movement should help gunnery. The flaps are easy to work, the landing gear is rugged and safe on unimproved runways, key parts interchange left and right, the plane's easy for ground crews to move around, the electrical systems generally keep failures from battle damage limited to the system that was actually hit, so you won't lose both gear and flaps from one bullet. You don't lose the guns unless you take damage to the gun system itself. You could of course lose the generator from one bullet, but you would still have the battery, at least for some period of time. This video is from the YouTube channel Patty Patron. For some reason when I copied it off YouTube it removed his watermark. I have no explanation for that. On his channel the video is much longer, it's in high resolution, great sound. Link in the description. He has a lot of great footage. This particular plane is a full-scale replica. The story of its construction is remarkable. Special thanks to Patty for allowing me to use his footage. Please check out his channel. Regarding the Wartime 190, we haven't even scratched the surface of this plane yet, but I really want to cover the 190 in detail. There are many videos out there about this plane, but I'm trying to do something a little different here and cover the stuff that others have ignored or didn't really explain. I started this video thinking I would get through all the features that showcased tank's cavalry horse design, and we didn't cover half of them. I think that's okay. I'll get the rest of them knocked out in episode 2. Sources for this video are a little more complex than usual. I normally like to put up the actual page on the screen of my source so that the viewers can see the evidence, or more importantly, go to the source book or document and know what words to search for so they can read more. I can easily do that with U.S. government documents and books because they're not copyrighted, at least not the ones I'm using. More than that, there's no moral issue with taking a page from, say, Pilot's Handbook of Aeronautical Knowledge or something similar, because those authors are paid a salary that has nothing to do with book sales. However, for this video, I had to use information from various copyrighted publications. The authors of these books spent a huge amount of time and effort on them. At least one of them actually interviewed Kurt Tank, which is where I got that Kurt Tank quote that made the racehorse versus warhorse analogy. I will of course list the books in the description, but I can't put images from the pages on the screen, hence the different look of this particular video. So that's about it. I'm really looking forward to making part 2. In fact, it's already well underway. I think it'll come out more quickly than usual. Anyhow, I hope you enjoyed this video. Have a great day and goodbye.